Okay, hello everybody, and let me show you how to solve this problem. The problem asks us to find the integral from 0 to infinity of the inverse tangent of x, all divided by x to the power of the natural log of x plus 1. And so remember, this at the bottom is actually equal to x to the power of the natural log of x times x. And we're dividing by it, so this actually becomes 1 over x. So and we have a factor of 1 over x and a natural log, so this really screams out for the substitution t equals to the natural log of x, because then we see that dt is going to be 1 over x dx. So we already have our dt up here, and this will become dt. Okay, so x will be equal to e to the t, and when x goes to 0, this thing t will go to negative infinity, and when x goes to infinity, t will also go to infinity. So if you call this integral I, we see that I will be equal to the integral from negative infinity up to infinity, the inverse tangent of x, and then we at the bottom this factor of 1 over x will this will go away. Natural log of x will become t, and x will become e to the t, so we get e to the t squared on the bottom. So we can write it as e to the negative t squared dt, and this should have been a t, of course. Okay, so now what we're going to do is we're going to send t to negative t, and you could use another variable to make this extremely rigorous, but we'll just use the same variable because we'll need it later on. So what would happen if we would send t to negative t, let t go to negative t? And what would happen? Our integral becomes, well, the bounds change, so we get the integral from infinity to negative infinity. Negative t squared is still t squared, so we get here e to the negative t squared, and negative t in parentheses squared, of course, and then the inverse tangent. This bit actually changes, so we get should have been an e to the t, of course, because there was an x, and x is e to the t, so the arctangent of e to the negative t, and then the differential becomes negative dt. Well, and this negative sign we can use to swap the bounds, so we get the integral from negative infinity to infinity of e to the negative t squared, arctangent of e to the negative t dt. Well, so actually not much has changed. Here we see the bounds are the same. We get this factor of e to the negative t squared, and this inverse tangent of e to the t and e to the negative t, that's the only difference. So that's actually quite interesting. And so what we're now going to do is we're going to add these two with each other. So what are we going to get? We'll get 2i, and 2i is going to be equal to, well, we have the integral from negative infinity up to infinity. We still got this factor of e to the negative t squared, and then we multiply that with the inverse tangent of e to the t added with the inverse tangent of e to the negative t. But remember that when you apply the tangent to something that is 1 over something that's actually pi halves minus the tangent of the thing you started with, and so you can use that identity to show that the inverse tangent of something added with the inverse tangent of 1 over that something, and well, of course, e to the t, e to the negative t is 1 over e to the t. Yeah, let's keep that in mind. To actually see that this will always result in pi halves. So that's quite nice. And then we recognize this famous integral. It's the Gaussian integral, and as we all know, it's equal to the square root of pi. You can show this with using polar coordinates. There's a really nice way of doing that, but I'm not going to do that today here. And so this is the nice Gaussian integral, and we find that 2 times our desired integral will be equal to, I'm going to make this pi to the 3/2 all over 2. So we found that our integral, which was and remember it was the integral from 0 to infinity of the inverse tangent of x all over x to the power of the natural log of x plus 1 dx, we found that it's actually equal to pi to the power of 3/2 all over 4. And that's our final answer. Okay, so I wish you guys a lot of math.